Reproducible scaling laws for contrastive language image learning. Abstract. Scaling up neural networks has led to remarkable performance across a wide range of tasks. Moreover, performance often follows reliable scaling laws as a function of training set size, model size, and compute, which offers valuable guidance as large-scale experiments are becoming increasingly expensive. However, previous work on scaling laws has primarily used private data and models or focused on unimodal language or vision learning. To address these limitations, we investigate scaling laws for contrastive language image pre-training with the public LAION dataset and the open-source OpenSeclip repository. Our large-scale experiments involve models trained on up to 2 billion image-text pairs and identify power law scaling for multiple downstream tasks, including zero-shot classification, retrieval, linear probing, and end-to-end fine-tuning. We find that the training distribution plays a key role in scaling laws, as the OpenAI and OpenSeclip models exhibit different scaling behavior despite identical model architectures and similar training recipes. We open source our evaluation workflow and all models, including the largest public clip models, to ensure reproducibility and make scaling laws research more accessible. Source code and instructions to reproduce this study will be available on GitHub. 1. Introduction. Large pre-trained models now achieve state-of-the-art performance on a wide range of tasks. In particular, large models have led to substantial advances in speech, language, vision, and multimodal language vision settings. A key ingredient in these breakthroughs has been self- or weakly supervised learning, which enabled the use of internet-harvested training sets and reduced the need for explicit human annotation of training data. In addition, recent pre-trained models relied on increasing the compute, model, and data scale by orders of magnitude. When varying model size, compute amount, and data quantity, several papers have empirically observed that both pre-training loss and downstream task performance reliably improve with scale. Specifically, researchers have postulated scaling laws in the form of power law relationships between model performance and model compute, or data scale. Such scaling laws allow practitioners to predict model performance for a given model and compute scale, extrapolate to larger scales, and can be used to determine pre-training regimes that obtain optimal model performance for a fixed amount of compute. Table 1. We study the scaling behavior of large clip models using fully open-source training code and data. All models in our investigation will be made available and include the largest public clip models. This table shows zero-shot performance at 224-pixel resolution, displaying accuracy on ImageNet, average accuracy on 35 VTab Plus datasets, and image retrieval recall at 5 on MS COCO image retrieval. So far, the literature on empirical scaling laws has focused on language-only or vision-only models. In the multimodal domain of language and vision, contrastive language image models such as CLIP have recently achieved large performance gains in zero-image classification, for instance improving zero-shot ImageNet accuracy from the prior state-of-the-art of 12% to 76%. Moreover, these models demonstrate unprecedented robustness to distribution shifts compared to prior supervised models. However, there is currently no systematic investigation for scaling trends in contrastive language image learning. One substantial challenge in this direction is that until recently, there were no datasets of sufficiently large scale openly available for the research community to undertake such experiments. In this work, we conduct a scaling laws study for contrastive language vision learning by utilizing the recently released LAION 5B dataset of 5 billion image text pairs. To ensure that our experiments are fully reproducible, we use the open-source OpenClip code to train clip models while varying model, data, and samples seen. We evaluate our clip models on several downstream tasks, including zero-shot classification, image retrieval, and fine-tuning via linear probing and end-to-end optimization. We observe a consistent increase in performance when scaling model, data, and compute, and derive scaling laws of power law forms across different downstream tasks. Interestingly, when comparing our OpenSlip and OpenAI's original CLIP models, we find larger scaling coefficients for OpenSclip models on zero-shot retrieval, while OpenAI CLIP models show stronger scaling for zero-shot classification. Table 1 shows two of our models and their results on image classification and retrieval benchmarks. We hypothesize that the training dataset is responsible for the task-dependent differences in scaling behavior between the OpenSLIP and OpenAI models. Our experiments have used the same VT architectures as the OpenAI models, and the training recipes are largely matched. The main difference in training recipes is the batch size due to different compute environments, and our experiments with varying batch sizes suggest that the batch size changes do not explain the change in scaling trends. Overall, our findings highlight the design of pre-training datasets as an important direction to further improve image-text models. Dataset designers should measure scaling behavior so that the generalization capabilities of image-text models can continue to improve as we increase model size and the amount of compute. Moreover, pre-training datasets should be evaluated on a broad range of downstream tasks because model scaling can differ substantially by task, with different pre-training sources leading to different scaling behavior by task. We hope that our open source and reproducible scaling trends offer concrete starting points for improving current image-text datasets and models. A. Relationship between total training compute and zero-shot classification performance on downstream tasks. Left, ImageNet performance. Right, average performance on 5 ImageNet robustness datasets. Scaling model size, data size, and samples seen leads to better performance on zero-shot classification. Models trained on OpenAI's web image text show a stronger scaling than models trained on Layon. B. Relationship between total training compute and zero-shot image retrieval performance on MS Coco, left, and Flickr 30K, right. Scaling model size, data size, and samples seen leads to better performance on zero-shot image retrieval. Interestingly, in contrast to zero-shot classification, models trained on Layon show a stronger scaling trend than OpenAI CLIP models trained on OpenAI's web image text dataset. Figure 1. Relationship between total training compute and performance in zero-shot classification, 1A, and retrieval, 1B. We fit a power law on the Pareto frontier of the available models. Since total compute budgets of different trained models are not exactly aligned, we divide the total compute scale into bins and select the best model performance from each bin. 2. Background and related work. Scaling laws for generalization and transfer. Strong empirical evidence that increasing model or data scale is beneficial was initially studied in the context of deep learning and computer vision. For instance, in 2006, the power law relation between scale and model performance was highlighted. Empirical work stimulated theoretical studies that provided justification for the observed generalization boost with scale, investigating generalization error in over-parameterized networks in the interpolation regime. References 6-9. Early empirical studies focused on the effect of training scale on upstream performance, measuring the test loss from the same distribution used for training. Subsequent studies of large language models, such as GPT-3, 8 demonstrated broad generalization capabilities in models with substantially larger scale. Moreover, neural scaling laws of the power law form were derived for language models, connecting model, data, and training compute scale to performance, 35-73-28. This also allowed accurate prediction of model performance at larger scales, and researchers were able to determine the scale parameters for achieving optimal performance given a fixed amount of compute, 28-39. Scaling loss studies were then also studied in the vision domain, 61-84, also observing a power law dependency of performance on scale. Scaling loss studies were also conducted for transfer and out-of-distribution performance, 35-73-84. In these studies, researchers observed that performance on downstream tasks benefits from increasing model, data, and training compute scale, 38-3, 35-84. Interestingly, upstream performance does not always correlate with downstream performance, 73-72. Since downstream performance most accurately reflects a practical use case, examining scaling behavior on downstream tasks is increasingly important. Recent work has also studied the effect of scale on other model characteristics, such as performance after pruning and compression, 64-11, and on susceptibility to catastrophic forgetting, 58. Scaling up language vision learning. Learning from very large amounts of weakly aligned image-text pairs has led to the development of models with broad generalization capabilities. Notably, work on contrastive language image pre-training, CLIP, 55 showed dramatic improvement compared to the previous state-of-the-art in zero-shot transfer and unprecedented robustness to distribution shift, 71, 48, 51, 18. The success of the initial CLIP study, which used a private WIT 400 image text pairs dataset and ViL14 as the largest scale vision encoder, motivated further developments and numerous extensions that increased model and data scale. Align 33 used a private dataset of 1.8B text image pairs and a large efficient net L2 as an image encoder. Basic 54 employed a large CoetNet 7 model with 2.4B parameters for the image encoder, also further increasing dataset size up to 6.6B image text pairs, using supervised visual encoder pre-training and private datasets Align and JFT5B. Lee 86 used a private dataset of 48M image text samples for contrastive learning on a total of 188B samples, scaling the visual encoder up to VTG14, which was pre-trained in a supervised manner using another private dataset, JFT3B. Coca 81 used VTG14 as a visual encoder, and both the Align and JFT private datasets and an additional text captioning loss based on autoregressive language modeling during pre-training. LeMoE 49 trained a sparse mixture of experts, MoE, single-tower architecture that share a common backbone for both vision and text, using both private 36B image text data from LeT and JFT48, obtaining a VH14 model at the largest scale. Flamingo 3 uses a large private interleaved image text dataset, using NFNetF6 as a visual encoder while scaling up the text encoder from 1.4B to 70B parameters. Pali 12 trained a multi-language multitask text image model using VIE 4B parameters as a visual encoder and an MT5XXL 38 parameters as a text encoder trained on a private dataset well with 29B image text pairs. While these studies already show clear merits of scaling up, they do not conduct a thorough scaling investigation by systematically scaling model, data, and training compute. Moreover, most studies involve a customized, multi-stage training procedure, where encoders may be pre-trained separately with unimodal losses and then tuned further with a contrastive image text loss, while also potentially freezing one of the encoders. This makes it difficult to derive conclusions about the effect of scale as pre-training procedures are heterogeneous. In addition, the private nature of the employed datasets impairs reproduction and validation of the results, especially in cases where pre-trained models are also not publicly available. Open large-scale language vision datasets. Conducting scaling law studies requires sufficiently large pre-training datasets. Earlier efforts to provide open image text datasets like MS-COCO, Visual Genome, YFCC100M, Conceptual Captions CC3M, and CC12M do not match the current scale of private data used to train large-scale language vision models. More recently, larger image text datasets have been collected from Common Crawl. The resulting datasets, Lion 400M and Lion 5B, are publicly available, enabling training language vision models at larger scale. Using the Lion toolset, it also became possible to construct additional open datasets, such as Koyo 700M. 3. Datasets and methods. 3.1. Open large-scale datasets. Lion 400M/2B. We use the Lion 400M and Lion 5B datasets, which are open, public image text datasets validated by the pre-training of state-of-the-art multimodal models such as CLIP and Stable Diffusion. Lion 5B contains an English image text subset of 2.32 billion samples, which we refer to as Lion 2B in this work. Due to its scale, transparency, and open-source nature, Lion has already been adopted by various works on language vision modeling, validating its use for large-scale model training and studies. 3.2. Pre-training open CLIP across various scales. To systematically vary model scale, data scale, and the number of samples seen during pre-training, we selected a scale range for each dimension. For model scale, we choose CLIP architectures with VitB32, VitB16, VitL14, VitH14, and VitG14 as visual encoders, scaling the text encoder in accord. For data scale, we use Lion 80M, an 80 million subset of Lion 400M, Lion 400M, and Lion 2B. For training duration, we choose 3B, 13B, and 34B samples seen scales. Due to compute constraints, for the larger H14 and G14 model scales, we conduct only restricted measurements. This selection provides coverage at the scale where we cannot afford to sample with the same density as at the intermediate and lower model scales. To verify that Lion 80M and Lion 400M are valid subsets of Lion 2B, we conduct a control experiment by extracting a random 400 μm subset of Lion 2B and comparing our reference OpenClip VIT-B32 models pre-trained on both datasets. When doing so, we found no significant difference. Compared to the original CLIP training procedure, we work with larger batch sizes and adapt the learning rate accordingly. We opt for larger batch sizes to allow for more efficient distributed training. Maximizing the local batch size per GPU and using close to 1,000 GPUs led us to global batch sizes in the range of 86 to 88,000 samples. In order to assess the validity of reusing measurements obtained with different batch sizes, we perform a number of control experiments varying batch size from 32,000 to 88,000 and observe a difference of 0.2 to 0.5% across different settings, which is small enough not to confound observations on the effective scale. For each number of samples seen scale, we execute a separate training experiment with a cosine annealing learning schedule adapted to the number of samples. This allows us to assess performance of models pre-trained with different training durations and avoid suboptimal training when using the same schedule for runs of different lengths. We tune a small number of hyperparameters, each scale point, to optimize validation loss and prevent training instabilities, and otherwise closely follow the original CLIP training procedure using the info NCE loss, atom with decoupled weight regularization, that is, atom W as an optimizer, with beta 1 equals 0.9, beta 2 equals 0.98, and weight decay of 0.2. We train the models using mixed precision. For larger model scales, we observed loss spikes during training, which had an adverse effect on performance. We fixed the issue by switching from mixed precision with float 16 to mixed precision with B-float 16. We hypothesized that B-float 16 fixed the issue due to larger models typically showing larger activation values as observed by making B-float 16 more suitable with its wider dynamic range, 8 exponent bits. CLIP pre-training experiments on larger scales require distributed training, as otherwise experiment execution times are intractable. We use OpenSlip, an open-source software that was adapted for distributed training on supercomputers. Using data parallel training via PyTorch DDP, we conduct experiments with up to 5,120 NVIDIA A100 GPUs. Distributed training was executed on Jewel's Booster, the supercomputer at Wellick Supercomputing Center, and partly also at Stability AI AWS supercomputer. For more details on distributed training procedure and on experiment compute budgets and runtimes, see Appendix Section A and Appendix Section B, point 2.4. 4. Scaling laws for different downstream tasks, 4.1. Zero-shot transfer and robustness. One of the biggest advantages of open vocabulary models like CLIP is that they can be used on downstream classification tasks by carefully designing text prompts corresponding to class descriptions without requiring any labeled training example. Moreover, pre-trained CLIP models are observed to excel on out-of-distribution robustness benchmarks, including an investigation on robustness benchmarks. We evaluate the models on ImageNet, ImageNet distribution shift datasets, and the Visual Task Adaptation benchmark. We conduct a simple duplication check for downstream datasets based on the perceptual image hash library phash, revealing no or very little overlap with pre-training datasets. Evaluation setup. We follow the setup of Radford et al. For each downstream dataset, we use a set of predefined prompts for each class, which we collected from prior works. We compute the embedding of each class by averaging over the embeddings of the prompts obtained using the text tower, then we L2 normalize them. Given a dataset, we classify each image as the class that has the largest cosine similarity with the L2 normalized image embedding. We evaluate the models using top 1 accuracy. For comparison to OpenAI Clip, we take VIB32, B16, and L14 models pre-trained on the private WIT400M dataset. Effective scale. Accuracy consistently improves when increasing model, data, and samples seen scale hand in hand. Accuracy follows power laws, such that larger models benefit from larger data and samples seen scale. The strongest ImageNet accuracy, 78%, is obtained with the largest total pre-training compute, using VTH14 pre-trained on Leon 2B data scale and 34B samples seen. For additional results, see Appendix Section B.4. Fitting power law, open clip coefficient equals -0.11, and alpha clip equals -0.16 for zero-shot top 1 ImageNet, and open clip equals -0.13, and alpha clip equals -0.24 for ImageNet robustness datasets performance. For those tasks, we observe a scaling advantage for clip pre-trained on WIT400M over OpenClip pre-trained on Leon 400M2B. OpenClip is similar for ImageNet and robustness datasets, suggesting that improving accuracy with scale leads to corresponding improvement on robustness benchmarks for OpenClip pre-trained on Leon. We also find bottleneck effects when scaling. For instance, OpenClip VIB32 and VIB16 models show no change or deterioration of performance when increasing data scale from 400 mm to 2B when using a smaller sample scene scale, 3 billion or 13 billion. Moving to the largest sample scene scale, 34B, then shows clear improvement for the larger 2B data scale, indicating that the number samples seen is a bottleneck. Using the obtained power law, we can make a prediction for the performance of a well-tuned VITG14 model when using the largest data scale of 2B and samples seen scale of 34B, giving us error estimate of 20.9%, 79.1% top 1 accuracy on ImageNet. We predict even stronger performance at larger scales. For instance, assuming 68 billion samples seen, we estimate top 1 accuracies of 79.7%, 80.7%, and 81.9% for VITH14, VITG14, and VITG14 respectively. 4.2. Retrieval. Retrieval is another common way to evaluate zero-shot capabilities of the models. In this section, we study the effective scale on both text and image zero-shot retrieval. Evaluation setup. We compute text-image scores using the cosine similarity between image and text embeddings and rank the top K images, response text captions, for each text caption, response images when evaluating on image, response text retrieval. We evaluate on MS Coco and Flickr 30K, following the evaluation setup and test splits from. We use recall at K as an evaluation metric where K equals 5. Effective scale. Again, we observe performance consistently improves when increasing scale following power law trends. We measure scaling coefficients OpenClip equals -0.08 and alpha clip equals -0.05 for zero-shot retrieval on MS Coco, and OpenClip equals -0.19 and alpha clip equals -0.10 for Flickr 30K. In contrast to zero-shot accuracy, retrieval performance shows a scaling advantage for OpenClip pre-trained on Leon 400M 2B over clip pre-trained on WIT 400M. We also observe scale bottleneck effects. For instance, OpenClip VEL14 model shows almost no improvement on Leon 400M when increasing the number of samples seen scale from 13B to 34B, indicating a data scale bottleneck. When increasing data scale to 2 billion, we then observe clear improvements when going from 13B to 34B samples. Figure 2. Scaling model and data size leads to lower error linear classifiers on ImageNet and CIFAR100 in both the few-shot and full dataset regime. We train linear probes for models with at least 13 billion samples seen. Also see corresponding Table 4. As discussed in Figure 1, we fit a power law on the Pareto frontier of the available models. Figure 3. Scaling model and data size leads to lower error linear classifiers on the Visual Task Adaptation Benchmark, VTAB. We train linear probes for models with at least 13 billion samples seen. Also see corresponding Table 4. As discussed in Figure 1, we fit a power law on the Pareto frontier of the available models. 4.3. Full and few-shot linear probing. Another common way to measure the quality of learned representations is by training a linear classifier. While this technique underperforms end-to-end fine-tuning, it is often preferred because it requires far less compute. In this section, we train linear classifiers, also referred to as linear probes, on the frozen representations of various clip models and examine the effect of data and model scale. Evaluation setup. Given a clip model with an image tower phi, our goal is to learn W such that W transpose phi of X classifies X as its label Y. Given a dataset, we begin by saving the image features and labels for the dataset. That is, for all image label pairs XY in the dataset, we cache phi of XY. We then train a linear classifier W to minimize the cross-entropy loss between softmax W transpose phi of X and Y. In preliminary experiments, we found that this softmax regression achieved higher accuracy than linear regression. We use mini-batch stochastic optimization with the Atom Optimizer. We use batch size 256 and select the best result in a hyperparameter sweep over learning rate and epochs individually for each model and dataset. For the ImageNet and CFAR 100 datasets, we consider 10-shot, 25-shot, and full dataset linear classifiers. Additionally, we train linear classifiers on the visual task adaptation benchmark. Effective scale. For ImageNet, CFAR 100, and VTAB, scaling up consistently improves the accuracy of a linear classifier. For ImageNet and CFAR 100, this is true in both the few-shot and full regimes. Moreover, among models trained on the same data distribution, scaling up follows a linear trend on a log-log plot. These results are perhaps not too surprising given similar observations of few-shot and zero-shot downstream tasks seen in previous sections, as well as the correlation between zero-shot and linear probe performance observed by Radford et al. Nonetheless, this result reaffirms that scaling up model and data size leads to continued accuracy improvements. 4.4. Fine-tuning. Next, we evaluate the effect of scale on fine-tuning performance. Since fine-tuning is much more compute-intensive than zero-shot and linear probing, we only evaluate a subset of the pre-trained models. Evaluation setup. We fine-tune and evaluate on ImageNet with the TIM library, using the image encoder from clip models trained on 2 data, 34 billion samples seen scale. To get the best results, we consider 2 different schemes: fine-tune directly on ImageNet, or first fine-tune on a subset of the full ImageNet 22K, we call ImageNet 12K, then continue fine-tuning on ImageNet, similar to earlier work. We compare the results with OpenAI clip models fine-tuned with the same settings, evaluating the models using top 1 accuracy on ImageNet and the ImageNet distribution shift datasets. The OpenClip models range from 82.6 to 88.5% top 1 on ImageNet, comparable to the best released ImageNet models pre-trained on public datasets. For additional details including strong supervised baselines, see Appendix section. In addition, we fine-tune and evaluate on 8 diverse datasets where zero-shot models perform poorly. We fine-tune a single model jointly on the 8 downstream tasks, and we end up with 12,000 classes, 12 million training examples, 470,000 validation examples. Figure 4. ImageNet and ImageNet robustness datasets classification performance for fine-tuned models. Figure 5. Scaling model and data size leads to lower error after jointly fine-tuning on 8 downstream image classification tasks. In this experiment, we fine-tune a single model jointly on all 8 tasks, alternating batches from each task. We fine-tune only the parameters of the vision encoder, using a fixed classification head for each task, initialized with the weights from the zero-shot model. Following Ilharco et al., fine-tuning only the parameters of the vision encoder. The classification heads for each task are obtained using the zero-shot text encoder and are kept frozen during fine-tuning. We fine-tune for 2,000 iterations with a batch size of 128, learning rate 1e-5, and a cosine annealing learning rate schedule with 200 warm-up steps in the Atom W optimizer with weight decay 0.1. We further explore the effect of fine-tuning on zero-shot ImageNet accuracy in the Appendix Section B. 2.2. Effect of scale. For ImageNet fine-tuning, only the models with the largest data and samples seen were fine-tuned. Despite the narrower scale range, a similar relationship in the slope of the OpenAI slip versus OpenSlip fit lines is observed across the model scales, Figure 4. Moreover, scale consistently improves accuracy when fine-tuning on other downstream tasks. Figure 5. While trends vary with the task, we find that the slope of the linear trend relating accuracy and total compute used for pre-training depends on the pre-training dataset, typically favors CLIP-WIT 400M, as we observe in zero-shot experiments. 5. Discussion. Larger scale improves performance across different downstream tasks. In line with previous studies, our work observes scaling laws of power law form across various downstream tasks. We empirically find that scaling model, data, and training samples sees results in consistent improvements on downstream zero-shot classification, retrieval, linear probing, and fine-tuning performance. We also observe bottleneck behaviors that occur when fixing one scaling dimension while increasing others. For instance, OpenSlip VIT B32 and VIT B16 are bottlenecked by the number of samples seen at the 13 billion scale. Increasing the number of samples seen to 34 billion reveals that Lion 2B brings clear improvement over Lion 400M, which would remain hidden when fixing the number of samples seen scale to a lower value. Similar observations may occur along other scaling dimensions. OpenSlip VIT L14 shows an example of data scale bottleneck on Lion 400M scale, as increasing the number of samples seen from 13 billion to 34 billion does not lead to improvements. The benefit of using a larger number of samples seen is then revealed when going to the larger Lion 2B dataset. Having derived scaling laws from our experimental observations, we are able to make predictions for both smaller and larger scales. Extrapolation has its limits, as saturation effects at both lower and higher scale ranges have been previously observed. We can, however, extrapolate to scales close to the ones we have already measured. A prediction for larger VTB14 trained on Lion 2B with 34 billion samples is an estimate of 79.1% ImageNet Top 1 accuracy. This may appear at first sight modest compared to results reported by BASIC 85.7%, LIT 85.2%, or COCA 86.7%. However, these works leverage an internal JFT dataset with labels which can be used for supervised pre-training. Moreover, for 973 out of 1,000 ImageNet classes, researchers were able to manually identify a correspondence from a JFT class. These works also use larger encoders, larger private data, and pre-train the encoders in multiple stages. Nonetheless, we estimate based on our empirical findings that further increasing model and data scale could result in competitive models even without using labeled data, additional supervised pre-training stages, or additional losses. Finally, we observe that the improvement of zero-shot ImageNet accuracy due to scaling up is accompanied by closely aligned improvements on robustness benchmarks. Scaling behavior depends on task type and pre-training dataset. When measuring scaling coefficients for the observed power laws, we see that OpenAI CLIP and OpenCLIP have distinct scaling advantages over each other depending on the downstream task. OpenCLIP pre-trained on Lion 400M 2B data has stronger scaling trends for zero-shot retrieval, while OpenAI SLIP, pre-trained on private WIT 400M data, shows stronger scaling for zero-shot ImageNet classification. We hypothesize that the observed differences are due to differences in the pre-training data, as we closely follow the architectures and pre-training recipes used for the OpenAI CLIP models. WIT 400M may have a stronger affinity to ImageNet as a result of the curation procedure, while Lion 400M/2B was filtered by a pre-trained OpenAI VITB32 model relying on its similarity measurements for image-text pairs, which may have rendered the dataset more suitable for retrieval-based tasks. This hypothesis can be tested by systematically varying dataset composition procedure, for example, by using a stronger L14 model for filtering crawled data and observing the effect on scaling behavior across various task types. Limitations of the current study. Observed scaling laws are based on points we were able to obtain with available compute resources. Therefore, the density of sampling the scale space is low. It is also not possible to conduct full hyperparameter tuning, especially on larger scales, due to high compute costs. We rely thus on control experiments that look at few hyperparameters at early pre-training stages, and on tuning already performed in previous work to suggest that pre-training for each scale is not far from optimal. It was also not possible to obtain more points for OpenAI CLIP due to the private nature of the WIT400M dataset. Moreover, we conduct only a simple duplication check for downstream data, which may leave few duplicates undetected. Previous studies also reported that duplication in test sets do not significantly alter most results, potentially due to the very large scale and diversity of pre-training data. 6. Conclusion. We present a systematic study of scaling laws for contrastive language image learning, investigating how scale affects performance on several downstream tasks and across adaptation methods. We find, in accord with previous works on unimodal learning, a power law relation between scale and downstream performance in a broad range of settings, including zero-shot classification, retrieval, few and full-shot linear probing, and fine-tuning. Interestingly, the scaling behavior for OpenClip Layon pre-trained models and for OpenAI WIT400M pre-trained models differ, showing distinct benefits of one over another on different downstream tasks. We hypothesize that such task-specific scaling differences originate from the different pre-training datasets. Predictions for model performance on larger scales made on the basis of the scaling laws estimate an 8.9% zero-shot accuracy on ImageNet for a VIA-G 14th clip model trained on 68 billion image text samples from scratch. Our study opens many directions for further investigations. Obtaining more data points for smaller and intermediate scales can provide enough sampling density to better understand the optimal configuration of model size, dataset size, and number of samples seen given a fixed compute, similar to works such as scaling laws for robustness benchmarks can be derived when controlling for larger accuracies observed at larger scales. Further, treating vision and text encoder scales separately may lead to modality-specific scaling laws. A promising direction is to study the effect of the pre-training dataset on scaling behavior. Our observations so far hint that the data source may strongly influence task-specific scaling. This paves the road for studies on foundation datasets. Having open datasets and open-source tools at hand, such experiments can be conducted and reproduced in a common effort by the broader research community. Acknowledgements. We would like to express gratitude to all the people who are working on making code, models, and data publicly available, advancing community-based research, and making research more reproducible. Specifically, we would like to thank all the members of the Layon Discord Server 3 community that was pivotal for the effort to compose Layon 400 Beam and Layon 5B datasets, without which this study would be impossible, and OpenAI for making their pre-trained clip models publicly available. Page 13. We want to thank Hugging Face for providing hosting space for open datasets and models, and Stability AI for providing supercomputing resources and storage space. The authors gratefully acknowledge the Gauss Center for Supercomputing EV for funding this work by providing computing time through the John von Neumann Institute for Computing on the GCS Supercomputer Jewels booster at Jülich Supercomputing Center. We also acknowledge storage resources on Just granted and operated by JSC, as well as computing resources from the Helmholtz Data Federation. Further thanks go for support provided by JSC Supercomputing Facility Administration Team, especially to Damian Alvarez for his endurance and patience during the long demiking sessions on Jewels Booster. Special thanks goes also to Richard Venku, Stability AI, for his ongoing dedication towards enabling a HPC system and infrastructure around it that can be used by broad community of researchers and citizen scientists. This concludes the reading of Reproducible Scaling Laws for Contrastive Language Image Learning on Research to You. If you would like more papers added, please leave a comment. If you would like to be notified when more papers are available, be sure to subscribe, like, and ring the bell.